Okay, let's start the afternoon session, and Joao will be giving us his second lecture.
Thank you. So let me start by clarifying something about D equals 3 flux tubes in D equals 3 that I didn't mention yesterday. Well, so first of all, after hearing some of your questions, I think there was a bit of a confusion what D means. So let me just emphasize. So the flux tube is always 1 plus 1 dimension. It's always like a string-like object that has a 2-dimensional worldsheet. What I call here capital D is the dimension of the space-time where this flux tube lives. So in particular, D minus 2 is the number of transverse directions. So it's the number of flavors of Goldstone bosons, okay? So it's always scattering in 1 plus 1 dimension. So that's very important that everybody has clear in his mind. So flux tubes in D equals 3, it means there's just one transverse direction. There's just one type of particle. So this 2 to 2 scattering of this particle, we call it this capital S, and I also defined it like that in terms of a phase shift, delta of S. And then the effective field theory, I mean, in my conventions, meant that this started as over 4, and then the first non-trivial coefficient appeared at S cubed. And yesterday, we derived this bound that gamma 3 had to be greater than minus some number, 1 over 768. Okay, and one thing I didn't say was that if you want to saturate this bound, then there is a unique S-matrix. So the S-matrix, so this is saturated by e to the 2I delta of S, given by a very simple function, which is 8I minus S, 8I plus S. Okay, that's it. You can Taylor expand, and you will get gamma 3 to be this value. And that's the unique S-matrix that satisfies all the properties of being analytic in the upper half plane and bounded by 1 on the real axis, that starts like S to the 4 in low energy, close to S equals 0. And has gamma 3 at this value, okay? So one obvious property of this S-matrix is that this is a phase. When S is real, this is just a pure phase. So it means that this particular S-matrix doesn't allow for any particle production. So the probability of starting in 2 particles and ending up in 2 particles is 1. And as I also mentioned last time, that's actually incompatible with the flux tube theory, because one can compute using the effective field theory the probability of production 2 to 4, and that's non-zero. That's proportional to gamma 3 squared. Okay, so that tells you that this S-matrix cannot be the full story. It's the one that saturates this bounded level of 2 to 2. But it cannot satisfy all constraints if we think about, say, 2 to 4 scattering. Okay. Any question about this? Okay. So then we move to D equals 4, or actually here, for most of the discussion, for these equations, the numerics I will show you is for D equals 4, but for these equations, I left D arbitrary. So, so now you have to take into account the flavor indices. So here, you just from the the transverse symmetry, SOD minus 2, these are the possible tensor structures that can appear. And you can either write it in terms of tensor structures using this basis, sigma 1, sigma 2, sigma 3. So that's very convenient because that's the simplest basis to study crossing. When you permute particles, you permute the flavor indices and the momenta. So if you permute, well, I didn't write here, but I should have. Right, so there's also momenta, P1, P2, P3, P4. So if you permute P1A with P3C, for example, you interchange S and T, and you interchange A and C. So that gives you these crossing symmetry relations. On the other hand, unitarity is simpler if you go to a basis where you use projectors into the irreducible representations of SOD minus 2 that you get from the tensor product of two fundamentals. Okay? So you can have a singlet, a symmetric representation, and antisymmetric. And okay, these projectors are very simple. I showed you one yesterday. If you want, I can discuss at the end. And of course, in this basis, since this is a global symmetry of the theory, the reducible representation in the in state is the same as the out state. So it diagonalizes unitarity. So in a given channel, unitarity just tells you that the probability has to be less than 1. So that's what I wrote here. So this is true for each one of the representations. The 3 representations can appear. So so that's almost it. So we just have one more constraint, which is not yet. Which is the effective field theory. So that I also showed you last time. If you use effective field theory, you can predict this. Well, maybe I. So this part, the order S and S squared terms are universal. This is completely fixed just by the string tension, which I'm setting to 1, and just by the Nambu-Goto term in the effective action. And then the first, if you want, non-universal terms appear at order S to the cube. And we saw there are 2 terms, 2 possible ways of contracting 4 powers of the extrinsic curvature. And so here, this correspond to these parameters alpha 3 and beta 3 that appear in this expansion. Okay. In fact, at this order, you don't need to do you see, this is also, of course, the low energy effective field theory is also constrained by crossing. So this type of relations, what appears in one and the other, is also constrained by these crossing conditions here. Okay, so now the question is, given the conditions 1, 2, and 3, okay, on the functions, you can choose the functions, say, sigma 1 and sigma 2 to be your free functions that have to obey these properties. What are the possible bounds? Can you get some non-trivial bounds in alpha 3 and beta 3, or everything is possible? Okay? So that's the question. And I don't know, well, there's some partial bounds you can get by doing some smart crossing symmetric combinations that you can solve analytically, but I don't know of any systematic way of solving this problem analytically. So I will explain now a numerical method that allows you to impose all these constraints systematically and get the optimal bounds that follow from these conditions. Any question about the logic? Okay, so I'll write here. Okay, so this It's what we call the primal method. Okay, and then I will explain more briefly the dual method. Okay, so primal method is basically what we will do. We will explicitly construct solutions to this system of equations, and in these solutions, then we will try to take extreme limits of alpha 3 and beta 3. Okay? So how do we write solutions? Well, we have to parameterize analytic functions on the upper half plane. So what we do is just we map the upper half plane to the unit disk and then write some general Taylor expansion, some polynomial on the variable on the unit disk. Okay? So let me explain that in more detail. So we take the S complex plane, the upper half plane, and we map it to the unit disk. Let me call that variable chi. So this is the map. And we do it very explicitly. Okay, so here we chose this map, 4 minus is over 4 plus is. Okay, so this 4, you could choose 1. Was a bit better for our numerics to choose 4, but this is not very important. Okay, and if you follow this map, so the origin is mapped to here to 1 in the chi. So this is the point s equals 0, and the point s equals infinity is mapped to here. And if you want this positive real s is mapped here to the upper boundary of the disk, and negative real s is mapped here. Okay. So that's the map. So one interesting thing in this map is that here in the upper half plane, crossing and real analyticity imply this relation between 2 points in the upper half plane, s and minus s star. So these 2 points in the upper half plane, s and minus s star, get mapped here into complex conjugate points. Okay, so if you want, this is chi of s, and this is chi of minus s star. They are just complex conjugate. Well, you can, it's simple from the formula. So it means that a function that is symmetric, like sigma 2, it's a function that is symmetric under this operation. Here is just a real analytic function. Okay? It's not symmetric. It goes by complex conjugation between those 2 points. Here, it goes by complex conjugation between chi and chi star. So then for sigma 2, for example, it's very easy to write an ansatz for the function. We just write it as a sum of powers chi of s to the n with real coefficients. Okay? Let me call these coefficients Cn. And we sum from n equals 0, in principle up to infinity. And in the numerical procedure, we introduce here a cutoff and max, which is our numerical truncation. And then we will see how things converge when we increase n max. Okay. So that's our ansatz. And similarly for, say, sigma 1. The difference is that now sigma 1 doesn't have this real analyticity. So here you can put complex coefficients. So I'll write an and bn, so they are all real. And then, of course, sigma 3 is obtained from sigma 1 using this. It's not independent. Okay, I'll just use that form. Yes. These branch points here, yes. The branch point will be pushed, it's here now at the boundary of the unit disk. So if n max is finite, Of course, this is just a polynomial, so there is no branch point anywhere. Yes. Yes, you can add to this in some other problems, actually in the next lecture. In some other problems, we add some explicit terms, for example, some logs or S times logs, explicit to match some low energy effective field theory, and then we just add some extra stuff to be general ansatz. Here, it's actually not needed. You see, it's not needed because up to the order that we are interested, we want to bound the coefficients alpha 3 and beta 3. There's still no logs. The logs appear at order s to the 4. So here, actually, there's s to the 4 times log s. The corrections, the first logs appear here. So they are smaller than what we want to measure. So we don't really need to input them explicitly. But you can, if you input, then you will converge a bit faster to the numerical solution. But okay, there's a balance how much effort you want to do, because then you have to deal with them explicitly. Yeah. More questions? Well, one important point is that you should not write it as s log s. You should write some function of this chi that behaves like s log s here, but it's bounded everywhere, because otherwise to get the right log here, you will spoil infinity. So you have to be a bit careful about how you add these terms, but yeah. Yes. Yeah, so the claim is that as n max goes to infinity, I can essentially parameterize any analytic function on the disk. Yeah. But actually, it depends how you ask the question, right? At any finite n max, you will never have singularities because it's just a polynomial. But inside the disk, you can approximate any function arbitrarily close. Okay. Then at the boundary, at this, you really need n max equals infinity to create the branch point. So it depends exactly on which type of question you want. Okay, so now we had these three conditions. I numbered them, right? There's 1 is unitarity, 2 effective field theory, and 3 is analyticity. So how are we doing? So this parameterization solved 3, right? 3 is automatic in my ansatz for any. So these are the variables. If I take any real variable Cn, Bn, they solve crossing and analyticity. The effective field theory conditions, they're not automatic, but they are very easy to impose, right? You can just take now this formula with some n max, some fixed number, 10, 20, what you want. You Taylor expand close to s equals 0, and this will be some, and you match that Taylor expansion, okay? That will give you some linear constraints on these variables. Okay? So that's a simple linear constraint on the variable Cn, An, Bn in terms of this coefficient, quarter, alpha 2, alpha 3, beta 3. Okay? So that's easy. So it's some linear constraint. So unitarity is the hardest one, because unitarity, it's not a linear constraint, it's a quadratic inequality. But it's a quadratic inequality in, it's quadratic in these variables, right? Because to go from, so e to the 2I delta rep of s is linear in the variables An, Bn, Cn, right? Because it's just a change of basis from projectors to delta functions. So this is linear, therefore the condition of unitarity is just, so unitarity less than 1 is just a set of quadratic constraints that can be very efficiently implemented in a computer. So in fact, we use STPB, which is the semi-definite programming solver that David Simon-Zuffen developed for the conformal bootstrap. And it's perfect for this problem also. So the way we do it is we take a grid, a quadratic constraint, we take a grid of points. So we take a dense grid in S, going from 0 to infinity, okay? Well, of course, the grid becomes less dense as you go to infinity because you take a finite number of points, but that's how you impose unitarity. Okay, any question about the method? You can, I mean, you can really do it in Mathematica. Of course, if you do it in Mathematica, Mathematica is not very good at these optimization problems with quadratic constraints. So once n max becomes order 5, Mathematica will start struggling or something like that. But also depends on how dense your grid is. But you can just implement these constraints and ask for. Now, what you ask, you take. So for example, what do? We minimize alpha 3 at fixed beta 3, okay? So as I said, both alpha 3 and beta 3 are some linear combination of the variables, okay, from matching with effective field theory. So let me show you the results. So at fixed beta 3, for every value of beta 3, we minimize alpha 3, and we get curves of this form. So maybe I'll do some color. Well, I guess by hand it will look like a parabola or something like that. And let's say, so what happens is that, let's say this is for n max equals 10, and then you try another n max, say n max equals 20. So now you have more variables, so you have more freedom, so you can get a bit lower. So you get another parabola a bit lower. Let's say this is n max equals 20. And then you can continue, and I don't know, from 20 to 50 already, that almost doesn't change. So you see in this problem, you see pretty rapid convergence when n max increases. Okay, and well, if you want order of magnitude, this is like 10 to the minus 3 in this, with my definitions, is something like that. And similarly here. So this is alpha 3. Guess it's not very important what these numbers really are. And so this is the allowed region. So there's no upper bound, for example, on alpha 3, and this is forbidden here. And this is the shape of the bound. Questions? Yes. From everything, right? I imposed conditions 1, 2, and 3. Some were 3 was automatic in the ansatz, 2 was easier linear constraint, and 1 was the most non-trivial that you had to go to a computer. I don't know how to solve it analytically. Okay, so let me now just make some comments. So there's two things I want to do. I want to make some comments about the extremal solutions. You see, in this method, you don't know the solution here in the middle. It's not, you don't know what there are many S-matrices that can be here, but the S-matrices here at the boundary, they are the output of your numerical procedure, right? When you do this optimization, you get all the variables, AN, BN, CN, that optimize this problem. So you know the S-matrix, you can plot it. Okay? So that's one thing. We can analyze this S-matrix and see what physics they encode. And then I want to discuss how you can get this bound from another method, which is the dual method, which is more powerful. And in this Bootstrap story, it's good to understand both methods. Okay, so what's the best way to describe this? Yeah, so let me discuss what is a resonance before. What do I mean by a resonance? Because that's one of the things one can read off in these extremal solutions. So here, let me start this discussion. It's better to start this discussion with a mass gap. Okay, so suppose there is a mass gap. So lightest particle mass gap equals to m, and I'm scattering the lightest particle. Okay. So then, in this context, the S-plane, what is the analyticity we expect in the S-plane? So now the cut, the two-particle cut starts at 4m squared, right? That's the 2m is the minimal energy of two particles. So S is the square of the center of mass energy. So it starts at 4m squared. And then you can have a three-particle cut starting at 9m squared, right? The square of 3m. Okay. And of course, then you have the crossed cut. So in this case, so you still have, say, forward scattering. So T is still 0. So U is 4m squared minus S. So the crossed cut starts at 0. Okay, and then there's all the other cuts. And I mean, why am I talking about this massive case? Because in the massive case, it's very clear that you have here an elastic region, right? So this is the elastic region where you don't have any energy to produce three-particle states. So if you scatter two particles, necessarily you end up in two particles. So then in this region, unitarity for the 2-to-2 scattering is an equality. So in the elastic region, S square is equal to 1. And using real analyticity, you can write that as S times S dagger, and S is above the cut and S dagger is below the cut. Okay, so in the elastic region, you can rewrite that as S of S plus I epsilon times the scattering amplitude of S minus I epsilon equal to 1. Okay, for S between 4 and 9m squared. But now you see, now this is an equation and it's analytic in S, so you can just analytically continue this equation. So in particular, if you have some other color, maybe suppose you have a pole here in the second sheet, pole. So when you enter the cut, you'll find a pole in second sheet. Okay, so that's what we usually call a resonance, right? There is a pole just under the cut, and you just see a bump in your imaginary part. But now look at this equation. Okay, so S just below the cut and S above the cut, they are the same. So now if now one of them enters the cut, the other one will be on the first sheet and the other one will be on the second sheet. But this is an analytic equation, so this equality will be maintained. And so when one diverges, the other one has to vanish so that the product is one. Okay? So it means that if you have a pole in the second sheet, you will have to have a 0 in the first sheet because of the presence of this equality in the elastic region. Okay? So it means that on top, on the first sheet, you will have a pole, will have a 0, and okay, you will have it on both sides, either here and also here. Maybe I just mark it here, 0 on the first sheet. So, no. It's it's a resonance, so it has both real and imaginary part, right? Because it has imaginary part is the width, right? There is a decay rate, a decay probability for this particle. It's just a resonance. No, this epsilon here is just to say that maybe I do another picture perhaps. Okay, so okay, so now you have first and second sheet. And that equation says that if you are above times below, you are equal to 1. Okay, so the product of the function above and below the cut is equal to 1. But this is an equality. So now let's move in S anywhere in the complex plane. So for example, suppose this point goes here, then this point enters the cut and appears here. So the product of the function here by the function here is 1. Just by analytic continuous elastic unitarity relation. So if you find a pole in this sheet, you need to find a 0 there. That's the only thing I'm saying.
But you cannot analytically condition the region where real is greater than 9x.
I can. So I just have to enter through this window, but then from here I can go wherever I want. If there is a 0 somewhere, I mean, if there is a pole somewhere here in the second sheet, I will find a 0 there. Then if I come back again and cross the cut, I go to some other sheet, and here I go to some other sheet, then I will find a relation maybe between two different sheets, which are none of them are the first sheet. So that's a bit useless, but at least this I know. Epsilon, I mean, if you prefer, you can put like, this relation was for real S, it will be like S plus and S minus, but then you can drop the epsilons as long as you know where you are in S. And then it's analytic in S. Okay, like a pole here on top of the cut? That's not possible because you see, if on top of the continue you can only have resonances. If the amplitude diverges here, it already violates unitarity, right? It is bounded by 1. You cannot have a stable particle that interacts with a continuum. Yes. Yes, if you have another particle like between mass m and 2m, then maybe you have a branch point before 9m squared. That's what you're saying, like m1 plus m2 squared. Yeah, true. The elastic region might not be. I'm describing the case where there is the only stable particle is one of them. But as long as you have a mass cap, you always have an elastic region and the argument goes through. The range will be slightly different. You could have a pole, if you have a pole here, that's that's a stable particle. Yeah. Yes. Yes. It's a stable particle. Okay, let me go on, otherwise I will not say anything useful. So yeah, so that's basically what I want to say. Should I write this formula? Yeah, in fact, if you want to be a bit more quantitative, you can really write. So if you have, so if this pole, if it's a sharp resonance, so the width is smaller, much smaller than the mass, so you can approximate the S-matrix. So if the width is much smaller than the mass of this, MR, let's say, M of the resonance, then you can actually, in the neighborhood of this resonance, you can just approximate the S-matrix by the following: M plus I gamma over 2 square. Sorry, on the upper half plane, S minus M. Okay, so it has a 0 in the upper half plane at M plus I gamma over 2, and it has a pole in the lower half plane, but this is in the second sheet, right? When you are, so this is for imaginary part of S positive. This is how you would write the S matrix on the first sheet, close to a resonance. Yes. No, it's square root. Square root. The free part, the massless. I don't remember. I think it's still power-like. Maybe, do you remember? It's still power-like, right? I'm not sure. It's not logarithmic, I don't think so. We could compute this as some phase space, but I think it's still power-like. It's probably not square root. But... Why is that important? No, if I think the relation here is much more complicated, right? Because it's unitarity is not just two terms. There's also 2 to 2 plus 2 to 3. No, it's so then here it's more complicated. There will be other equalities, other relations, but it's much more complicated. It involves other functions, the S matrix 2 to 3 and things like that. Okay. Anyway, all this to say that I will take, since I have no access to the second sheet, I will take as the definition of resonance a 0 in the first sheet. Okay, and I will continue to use that definition even in the massless limit where the elastic region disappears. Okay, I take it by continuation of this picture, and it's still a good definition, because if you, I mean, you can also look at the phase shifts. For example, the S-matrix will still be well approximated by this, even in the massless limit. And you see that the phase shift jumps by pi when you pass close to this resonance. So the standard definitions of resonance agree with this definition that I'm using here, a 0 on the first sheet. Okay? So with that in mind, I can tell you where we have zeros in our extremal solutions. So let's see, what's the best way to plot this? Okay, so let me plot this region. So the most interesting region is this region here. And this is the most interesting region because it's the region that has the values of beta 3 and alpha 3 that seem to be compatible with the lattice data. Maybe Sergey will explain that after me. And at least you will explain about the resonance that I found here. So, so in this region here, we find resonance in this antisymmetric channel, also called sometimes axion. Okay, so this is the antisymmetric representation of this SO D minus 2, which, okay, if D is 4, so this is just SO2, it's a pseudoscalar. Okay, so that's why we can call it an axion. And so in that case, let me just plot here slightly, something like that. So if I plot the mass of this antisymmetric resonance and its width, in that region over there, you find that the width is actually much smaller than, so let me put this in some units. Okay, so this is, the units are always L string equal to 1. Something like that. And then there is a curve. Let me plot it. So it's much smaller. The width is much smaller than the well, maybe I'll do it like this. I'll do some color coding. Okay, like this. Okay, so this, the white is this part, and the orange is this part here. Okay, this is orange and this is white. So on the white region, you have a rather sharp resonance. So the mass is much bigger than the width. While once you go to the other side, then it becomes very broad. Basically, it's as broad as its mass. Okay. So that's this. So just to be sure, so this is S antisymmetric at S equals M NT plus I gamma over 2 is equal to 0. Okay, so we determine this is a 0 that moves when we move along that extremal solution. Is it clear what I'm saying? So that's one nice signature, because as Sergey will explain, from the lattice, there is evidence that there is such a sharp resonance on the flux tubes in 4-dimensional Yang-Mills theory. So that's suggestive that the Yang-Mills, so if you try to match what you get from the lattice, you can more or less put here and here the SU3 and the SU5 theory. Okay, more or less within the numerical errors, pure gauge theories. Okay. Yes. Yes. Yeah, I yes. Yeah. So that's, I mean, I already. So your question is, why do I keep defining a resonance as a 0 here, even though this elastic region disappeared, right? Went all the way to 0 in the massless limit. Yes. Yeah. Yeah. Yes, correct. Correct. Well, actually, that raises another question: is when you have a pole in the second sheet, does it appear in other sheets when you enter through other channels? And this is, I don't think this is a known fact. There is some lore, sometimes called nuclear democracy, that if a resonance exists, can be formed by the two particle channel, it can also be formed by the 3 and the 4 particle channel, as long as the charges are allowed. And of course, everything here has the same charges because it's appearing in the same scattering process. So from that principle, you would actually expect that the pole appears in all sheets. But I don't think this is known. I don't know if Sergey has some comment about this. But in any case, the presence of the 0, you will still see the presence of the 0 very nearby, and that will still make your phase shift jump by pi. So you will still see an effect on your physical S-matrix of the nearby 0. More questions? Yes. Good question. No. I mean, the effective field theory, yes, but the S-matrices don't assume any of that, right? I'm imposing conditions to arbitrarily high energy. So, okay, what you can complain is that something I forgot to emphasize is that these extremal S-matrices, besides having resonances, if you actually plot the modulus of, so the unitarity condition, you will see that as n max tends to infinity, they just saturate unitarity in the two channel. So indeed, they are not very physical because they don't allow for any particle production. So that, but we don't impose that, right? That's just the extremal solution chooses to do that. So I don't know by heart. I mean, in terms of order 1 number, it's all order 1, right? Because I'm measuring everything in terms of L string. But now, if you care about factors of 3 or 4, I don't remember by heart. Blue ball is 1.7. Thank you. Okay. Any other question? I think I said everything else. Okay, so now let me discuss briefly the dual method, because it's a bit more, it converges faster, and it's also in a way more rigorous because the finite truncation already gives you a good bound. Right? Because here you'd never really get a bound, right? As you increase n max, you increase your space, right? So if it converges, then you can get convinced that you're approaching a bound, but at finite truncation, it's never a bound, it's just some approximation to the bound. So the advantage of the dual method is that you approach the optimal bound from the other side. So let me try to explain how that works. So for example, let me just draw a picture to understand, to explain this idea. So far we did primal method. So what do? We rule in theory. So we get that and then get that and slowly start to approach some bounds. So this is what we do with primal. We rule in theories and we approach the exact bounds from above. Okay. Let's say at some fixed value of beta 3, that's the picture. So now I will explain a method that approaches from this side. So it rules out alpha 3 below this, and then below this, and then it approaches from this side. Okay. So if you know about the conformal bootstrap, that's how the conformal bootstrap works. In the conformal bootstrap, we always use this dual formulation, where at finite truncation of the constraints of conformal field theory on a 4-point function, we already get a good bound. And then we improve the truncation level and we get better and better bounds, which sometimes get very small and can isolate theories. Okay? But here, the first thing that we found out to do was this primal. So now we also understand how to do it on the other side, at least in 2 dimensions, for scattering in 1 + 1 dimensions. So what I'm going to explain is based on this reference I gave you yesterday by Joan Elias Miró and Andrea Guerrieri. Okay, so how does this work? So it's convenient to change from this scattering amplitude that is bounded by 1 to the more standard scattering amplitude, let me call it M of S. So this is like the separation S is equal to 1 + IT. Okay, let me call it M of S here. And okay, let me write this because it will be useful. So now if you use it's still here. Let me go back. Sorry, for simplicity, let me go back to z = 3. Otherwise, it's a bit too many things to write. Just to illustrate. So let me just write this expansion. Okay, so from effective field theory, you get this expansion. And now we want to formulate the bound. Sorry, let me put here gamma 3. Right? Let me think about the bound in D = 3 in gamma 3. We went all the way to -1 over 768. So with primal, so in this case, we could do it analytically, it was easy, but we could also do it numerically. And now we want to define a dual method, okay, to go from this side. So the idea is going to be to use this M and try to find a bound on this coefficient here that appears attached to the flow. Okay, and the first step is to rewrite the primal in a slightly different way, which I already did beforehand. So let me show you. You should thank me for saving your time. So some of them are obvious. The second one perhaps is less obvious, so let me explain it. So this is a rewriting of the primal method. So what we say is that the variables are these two functions, two real functions of a real variable s from 0 to infinity. And those functions are the real part of m and the imaginary part of m. So these functions, you first think of them as completely free, and they're just constrained by these 5 equations. And under these 5 equations, you minimize gamma 3, okay? So the first equation is just unitarity. So it's actually the way you know it better. So the optical theorem, the imaginary part related to the modulus square. So that's just, I mean, if you just replace S by that expression in terms of M, this follows, it's elementary. Then this one, I will explain a bit in more detail, but it's basically what analyticity gives you. It gives you a dispersion relation that relates the real part with the imaginary part. So that's what analyticity implies. And then the last 3 are just effective field theory constraints, okay? So these 3 come from the low energy expansion. So it tells you that the first coefficient s squared is a half, and the coefficient s cubed is 1/16, and the coefficient s to the 4 is related to gamma 3. And you get those coefficients using this kind of dispersion relations, integrating the imaginary part or the real part, depending if you want a real or imaginary coefficient, from 0 to infinity. Okay. So now you can also solve this problem just by parameterizing these functions, for example, with piecewise linear functions from 0 to infinity, and then imposing these constraints and minimizing gamma 3 subject to this constraint. But now in this form, this is going to be useful to formulate the dual problem. So that's what I want to explain. I have about 15 minutes, right? Until. Okay, so let me explain this dispersive constraint. So that's the usual trick, that to write a dispersion relation, we just use Cauchy theorem. So here there is a slight subtlety that we have to use some subtractions, because m, you see, s is bounded by 1, but m appears in s divided by s. So you can in principle grow linearly. So to make sure the dispersion relation converges, we do what we call a subtraction. Well, but let me explain exactly what that means. So let's take here this z complex plane. And now let's take S in the upper half plane. And let's just take a contour around it. Let's call this contour C. Okay. So if I do this contour here, then I just have a pole at S. So by Cauchy theorem, I take the residue, I get M of S. So it's a trivial identity. But now, of course, what I want to do is I want to blow up this contour. So I want this contour to go all the way to the real axis plus a big arc at infinity. 0. And now I can drop the arc at infinity, because this decays like z cubed, and m can at most grow linearly. You see, m can at most grow linearly because s is bounded. So I can drop the arc at infinity, so I just get this integral over the real line. And now I can break the integral over the real line between the negative and the positive part. So, and then use crossing. Okay, so let me do that. So 0 to infinity, dz over 2 pi I. So this is the positive part, and then the negative part, I would get m of minus z over z plus s. So this is what I would get from minus infinity to 0. But then I can use crossing to rewrite this guy as m of z. Okay. Right. And now the last thing you have to be careful to derive that form over there is that now when you send s was some point in the upper half plane, but now we want this formula when s is actually real. So you should approach the real axis from above because it comes from the upper half plane. So you just write s as s plus I epsilon. Okay. So here becomes s plus I epsilon, and here s minus I epsilon, minus s minus I epsilon. And so at this part, the I epsilon is irrelevant because z is positive and s is positive. Let's say s is approaching the positive real axis. So here it doesn't matter, but here, of course, it matters because you will have a pole on the real axis. So you can separate this into principal value and the delta function. And then you just take real part of this equation, take real part of this equation, and you get that equation. Well, should I write it? I mean, I think I don't need to write it, right? So I just use that the real part of 1 over z minus s minus, I just use 1 over z minus s minus I epsilon is principal value. That's what is written there, principal value of z minus s plus I pi delta of z minus s. Okay, and then I take real part and I obtain this equation. Okay, so here I have an I, so taking the real part, I get the imaginary part of m, and the real part, this delta function gives me m again, so I get m on both sides, so that's why I get this factor of a half of the real part, not the full. Oh, okay, that's some detail. So I hope you understand the logic of how to use analyticity to write a dispersion relation, and then you see, the beauty of this dispersion relation is that now it's a relation between functions, real functions of a real variable. Okay, so we're no longer talking about the complex plane. We derived a relation between a real function of s and another real function of s. So this is integrated for real z from 0 to infinity. S is real from 0 to infinity. Okay. Okay. So that's what analyticity gives you with this kind of dispersion relations. Now, how do you then formulate the dual problem? No, I should not erase this. So it's very systematic. You just have to define a Lagrangian, and you impose the constraints by introducing Lagrange multipliers. So you define a Lagrangian. So let me write it like this. L let me write it as M and lambda, which is a set of primal and dual variables. I will explain in a second. So these lambdas are Lagrange multipliers that impose the constraints. So these are just the effective field theory constraints. V4 of 0 minus C4. And then there are the constraints from the dispersion relation. So that's an infinite set of constraints, one for every positive real number, let's say Z. So dispersion of Z. And there's also the unitarity constraints, which are inequalities. So I introduce variables dual to every constraint. So now let me explain what do I mean by variables. So this M are the primal variables. So in this case are the real part of M of Z. So it's a function of variables, another function of variables, and gamma 3 if you want. I guess that's the way it's formulated here. So what you want to do, you want to minimize this Lagrangian, which is given by gamma 3 with respect to all these variables. So the lambdas impose the constraints that we had there, and these W's and mu also impose the constraints, and then you vary all these primal variables subject to the constraints. So the dual variables are the lambdas, lambda 2, lambda 3, lambda 4, and these functions, omega of Z and mu of Z. And the point is that omega of Z is just some real function, but mu is positive. Okay, because you have an inequality there. U of S is an inequality. So here you also have the corresponding Lagrange multiplier is a positive number. Okay, so yeah, so what is the logic for that? Is that yeah, if you don't put this constraint, then there's no minima, right? There is no lower bound for the Lagrange. Okay, and now okay, now the argument is quite simple. Well, let me write it like this. So what's the optimal problem? So the problem we wanted to, we are solving for the primal problem can be formulated as like this, well, infimum or minimum. Let me write it. Optimal geometry. This is okay, let me explain that. So this is what we've been doing so far. Primal formulation. So let me explain why this is true, okay? So first you maximize with respect to the dual variables. So if you do that here, so the variables that are real numbers, right? The lambdas and the W's, maximizing with respect to it basically just means imposing the constraints, right? So it imposes the equality constraints that you have there. And then maximizing with respect to mu. So if u, so let's see if I get this right. So if u was negative, then maximizing with respect to mu would be infinity, right? But for u positive, maximizing with respect to mu is just setting mu to 0, so this term drops out. So once you, so for all values, so if you don't respect the unitarity constraint, the maximum here is infinity. So then when you minimize, you don't get a useful bound. Okay? So once you minimize with respect to the primal variables, that means you only get, I mean, the minimum with respect to primal values will be obtained when you respect unitarity. That's the way to put it. Okay, I feel I'm not being very clear here. So yeah, it's hard to put in words, but it's a very simple statement that I'm making here. This formula is basically saying this first step imposes the constraint, and this second step is what we've been doing since the beginning, minimizing with respect to the variable. Okay, so that's the primal formulation. Now, how do you get the dual? The dual is just exchange these two. Okay, and that it's a known inequality called the max-min inequality. That if you exchange these two operations, that you first compute the minimum or the infimum with respect to m, and then the supremum with respect to the other variables of the same Lagrangian, then this inequality is true. Okay, so this is very easy to convince yourself that if you permute. So if you have a saddle point, then this is saturated. That you like one is to go through the valley to the highest point in the valley, and the other one is to go through the ridge to the lowest point in the ridge. So at the saddle point they meet. This is saturated, but in general, this is an inequality. And now this is what we call, so this, you see, by this first operation, you eliminate the primal variables. So you get some function that only depends on the dual variables, what we introduced as Lagrange multipliers. And now, whatever value of capital lambda you put here, it's already a bound, a lower bound on what you wanted to find. Okay? So whatever truncation you do on your dual variables, once you have this dual functional, so this is what we call the dual functional, one has a valid bound on the minimum possible value of gamma 3. Okay, so that's how it works, and it turns out that this is, in almost all problems that we've tried, this is a much more efficient way to approach the optimal bound. Okay, any question? So it's a bit abstract. Okay, so in practice, what happens is that if you play this game, then here, I already used all colors. Some red, some pink. In practice, if you now play this game, you will get bounds like that. Okay, so this is dual, where you exclude. Okay, so everything that is below is, so in the dual, once you implement it numerically, you also have to put some numerical truncation, but any truncation that you give there will give you a good bound. And then as you improve, you will approach the bound from below. Okay, and for this problem, and generically in all cases that I know of, the dual approaches the bound faster, more efficiently. Okay. Okay, I'm out of time. I'm out of time. Okay. Maybe can I take 1 minute to say some future directions, so that I talk about Pyans on Friday. So okay, so today now this part was more about methods, that we have primal and dual. So this in 2 dimensions is very well understood. In higher dimensions, not so well. There are some dual methods, but they have several limitations. We can perhaps discuss more of that on Friday. But going back to this flux tube story, what else would you like to do? So we did the simplest possible observable, which is 2-to-2 scattering of these massless Coulson bosons. So we are thinking about other observables. So for example, with Aditya and Andrea Gaghieri, we are thinking of a mixed system where you can have a flux tube and glue balls scattering against the flux tube. Okay, so now you can have other amplitudes where glue balls go across the flux tube, or glue balls decay into two of these Brannons into the flux tube, and vice versa. And that gives you access to new observables of how glue balls interact with the flux tube. Okay? So that, of course, only makes sense in a finite end theory, but say for SU2, that looks like a very good observable to look at. Another thing is just from intrinsically from the flux tube perspective, one would like to go to not just 2 to 2, but 2 to n, right? or n to m scattering amplitudes. And in general, that's very difficult in scattering amplitudes because the analyticity structure is in general not very well understood. But in this specific case of 1 plus 1 dimensional quantum field theory with massless particles, it's actually very simple, right? Because if you have massless particles in 1 plus 1 dimensions, they can either move to the right or to the left at the speed of light. So if you have two massless particles moving to the left at the speed of light, it's still a massless particle, right? It's just P1 plus P1 is still null. It's just the same null vector. So what you can do is to take, say, a pair of particles and now define a wave function on the fraction of momenta of the total momenta carried by one particle. And in fact, you can define states, which we call jets, which are just as good states as the original massless particle, just labeled by an extra quantum number that tells you the wave function of this fraction of momentum that each one carries. So in fact, one can set up a bootstrap of 2 to 2, 2 to 4, and even 4 to 4, just by considering these jets of two particles, which act like a massless particle, just with a new, just like many flavors of massless particles. And all of these are constrained by the effective field theory, by the same effective field theory. So now you can get more constraints and more observables on this flux tube S-matrix. Okay, so this, you can ask Alexandre about this project. He has all the plots of what we're trying to do, also with Pedro and Andrea Gajeri. So these are the two things we're trying now in the flux tube story. I guess one big question is, besides this effective field theory coefficients, what kind of observables, what kind of questions would be interesting to bound in these theories? Yes. We impose that they are all coming at low energy from the same effective field theory. So so that's more or less automatic. Well, okay, you say if I keep some particles hard and just one soft, that would be stronger. That in our setup we cannot really do, because we make these jets, so the two particles are in some particular wave function for the momentum fraction. So we cannot just take, like inside the jet, one particle to be very soft and the other very light, because that would require to go to infinite number of flavors, if you want, of these massless particles. But that yeah, that's, I think, beyond what we are able to do now. That's a good comment. More questions?